Good day. I'm Norman Wildberger, and today we're going to start talking about the basics of algebra. And we're going to start off with a very simple algebra, the kind that students learn in public school. This kind of algebra involves unknown quantities, which are denoted by letters, usually the letters at the end of the alphabet, like X, Y, and Z. So for us now, X is an unknown number, and we're given an equation like this one. X plus 2 equals 7. So it's a game. If you have a 10-year-old daughter, like I do, you can ask her, well, if X plus 2 equals 7, what is X? And she'll think for a little while and figure out that X equals 5. If I give her a slightly harder one like this, it might be a little bit more challenging. X plus 13 equals 41. But eventually she might figure out that X equals 28. However, with a more complicated question like this involving bigger numbers, X plus 378 equals 642, how is she going to figure out that the answer is 264? Some kind of manipulation of the equation is necessary to reduce it to a simpler equation. And it turns out that although the original equation involves addition, the actual solution of the problem uses subtraction. So if we start off with X plus 378 equals 642, the way we solve that is by rewriting that equation in this form. We bring the 378 on this side to the other side where the plus sign turns into a minus sign. So that's how we can then calculate that X equals 264. And these two equations are considered to be equivalent in the sense that if we have a solution to this one, then it's also a solution to this one. And conversely, if we have a solution to this one, then it's also a solution to this one. And this is a basic strategy in algebra, even in more complicated algebra, to take an equation involving some unknowns and to simplify it to get an equivalent equation which is easier or simpler to solve. Here are some other examples. Y minus 5 equals 3, illustrating that the variable doesn't have to be X. It could be Y or Z or anything else. And in this case, there's a minus 5 on the same side as the Y, and so we like to bring the minus 5 to the other side where it becomes a plus 5. So we get Y equals 3 plus 5, which of course is 8. How about this equation? Z plus 10 equals 2. Well, if we bring the 10 to the other side with a minus sign, we get Z equals 2 minus 10. But now the answer is minus 8. And we see that even if we start with a problem involving only natural numbers, the solution might very well take us into the realm of the integers. So in general, for this kind of equation, we need to consider our numbers to include integers. Now let's have a look at some slightly more sophisticated problems. Suppose we have the equation 3x equals 12. And our convention is, and we have to be clear about what the convention is, that 3x means 3 times x. So you can see why we might use this convention, because if we're using x as a variable, then it can easily get confused with our multiplication symbol. So when we write 3x, it means 3 times x. Or similarly, 3y means 3 times y, and so on. All right, well, if 3 times x equals 12, then if you know your multiplication table, x equals 4, because 3 times 4 is 12. If 7x equals 49, then from your multiplication table, x equals 7. But if you have 19x equals 893, your multiplication table probably doesn't go up that far, so you don't just automatically know what the answer is. And so although the question involves multiplication, the solution uses division. In other words, we take this equation, 19x equals 893, and we replace it with the equivalent equation obtained by dividing both sides by 19. So if we divide this by 19, we just get simply x, and if we divide this by 19, well, we get that fraction. And 893 divided by 19 turns out to be 47 once you do the long division. Here are some other examples in the same kind of spirit. 4y equals 36. Well, then y equals 36 over 4, and that's 9. Here's another example. 5z equals 11, say. Dividing by 5, we get z equals 11 over 5. But now, as opposed to the previous cases, 11 divided by 5 is not a natural number or an integer. So we must remain with this quantity as simply a fraction. So this kind of question generally requires us to extend our number system to include rational numbers, fractions or rational numbers. I recall that fractions for me are always positive, and rational numbers can include negative fractions as well. So we can use both of those types of equations and put them together to get somewhat more complicated examples. For example, 3x plus 4 equals 11 minus 2x plus 8. That's a single equation in an unknown variable x. So the assumption is that this variable x and this variable x represent the same mystery number, and we have to find out what that mystery number is. And what we generally do is we replace this equation with a series of equivalent equations obtained from this one by standard operations. Generally speaking, we try to get all the x's on one side and all the numbers on the other side, and then we try to simplify everything until we finally have x equals some number. So in this case, 3x, the 2x on this side becomes a plus 2x when we bring it over there. We have 11 plus 8. The 4 here becomes a minus 4 when we bring it to the other side. So 5x equals 15 and x equals 3. Another example involving some fractions involving our unknown variable x. 6x minus 1 divided by 2 equals 5 plus 3x divided by 7. And x becomes the fraction 17 over 36. Manipulation of these kinds of algebraic equations rely heavily on a prior understanding of arithmetic with fractions. Okay. If you don't know how to do arithmetic with fractions fluidly, then you're always going to struggle with algebra. And this is a very important point. Okay. It's one reason why get rid of those calculators when you're teaching students mathematics. Force them to work with pen and paper to become confident and skilled at arithmetic with fractions, because it's the basis for moving to algebra. So here's a fun little party game that you're all probably familiar with. So let's look at a particular example. Suppose that we're asked to pick a number and say add 3. So we're going to think of our number as being x. Instead of 7 or 12 or whatever, just think of it being an x. This turns out to clarify what's going on. So after we've added 3, we have x plus 3. Suppose the next instruction is to multiply it by 2. Well, 2 times x plus 3 is 2x plus 6. The next instruction is add 10. Alright, so then we have 2x plus 16. And the next instruction might be to subtract 4. Well, then we have 2x plus 12. And then we are told to divide by 2. Well, if we divide 2x plus 12 by 2, what we're going to get is x, because 2x divided by 2 is x, plus 6, because 12 divided by 2 is 6. Okay, and then finally we're asked to subtract our original number. So there's the number we got right now. The original number was x. If we take x plus 6 and we subtract x, then we end up with 6. And you can see that, yes, the answer is 6. It is independent of the number x that you started with. Next time we're going to have a look at solving quadratic equations, which is a big step up from these linear equations we've been looking at so far. But it's still part of baby algebra. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.